Okay, in the second part of this double lesson, what we're going to do is look at the derivative graph, or the graph of the derivative function, the gradient graph, the graph of f dash x, heaps of different ways of saying what we're doing. But first of all, we'll look at what we call increasing and decreasing functions. And I've said here that the term strictly increasing and strictly decreasing is not well understood and is tested by examiners at 3-4s often. In fact, in 2019, there was a question on a strictly increasing or a situation where it involves strictly increasing. I think about 5% or 10% of the state got right. It was a really tricky problem. Okay, so here is a classic problem. This was off an 11 methods exam a few years ago. So for the graph shown below, find where the graph is strictly increasing. Okay, so what we can see here is we've got increasing here because as x increases, y increases, and it seems to happen all the way up to the turning point there, and it also increases beyond that point there. Okay, so that's x equals 2 there, and that's x equals -2. So most students would say something like this: it increases when x is less than -2 and x is greater than 2. Okay, that's where they say. So this here would be the most common answer I get to this problem, and it's actually incorrect. That is not correct. So this is the correct answer. All right. Now, why is it? Well, actually, the definition of increasing or strictly increasing is you basically have to consider taking 2 points over a particular interval and compare the y values generated. And if the y value of the second point or the larger point is larger than the y value of the smaller point, then you've got a strictly increasing situation or an increasing situation. Now, here's my example. Just say I take this point here, point A. That's got this value down here. Just say I take this point B. I get this y value here. Now this y value is bigger than this y value. Okay, so that means that we've got an increasing situation between A and B. Now that will happen if I retain point A and choose point B. It'll happen all the way up to and including the stationary point or the turning point here. Okay, so what we're going to say is it's increasing from -infinity all the way up to the stationary point, but inclusive of the stationary point as well. All right, and the reason also for that is if I choose a point infinitely close to the stationary point on the left, but not actually touching it, there would still be an increase at the stationary point. What I can't do is select the stationary point and select the stationary point because I can't increase or I can't detect increase at a point. It's got to be between 2 points. So the correct answer is this because it's got to include the stationary point in the domain over which it's strictly increasing. And same goes over here. It increases from 2 inclusive all the way up to positive infinity. So to understand why -2 and 2 are included, let's consider a more basic graph. Consider the graph of y equals x squared. When is the function strictly increasing? Again, most students will say, oh, it's from 0 onwards, but you can't include 0 because that's a stationary point and there's a 0 gradient there. But actually, I'm not asking whether it's a stationary point or not. I'm asking whether I'm going to get an increase. And so the first point you're going to say is, all right, let's start at 0 and choose any point in the positive direction of x, any point you like. Let's go with this one here. That's going to be a positive y value. This is a 0 y value. This is larger than this. Therefore, it's x greater than and equal to 0. Okay, so what is f of 0? It's going to be 0. And what is f of x, where x greater than 0? Okay, it's always positive. Thus, between 0 and x greater than 0, it is increasing. We can write it in an interval, and that's the more common way you'll see it, is 0 to positive infinity, inclusive of the 0. So when is it strictly increasing? So many students will say something like this. It's -infinity, non-inclusive, all the way up to 0, but it looks to be like I've taken 0 there and included it on the right side, so I can't include it from the left side. No, you can. You absolutely can. It increases where x is an element of negative infinity all the way up to 0 inclusive. Because again, if you think about it, take any point to the left of 0 here, all the way up to and including it, you'll get a decrease in the y values. All right. Drawing gradient graphs is a skill that requires persistence in developing. Once you get it, you can be safe in knowing that you really understand differential calculus. So if you can do this, you're sorted. It comes up all the time as well. All right, so how do we draw a gradient graph? Well, I think that the really important thing to do is that you need to talk to yourself a little bit, okay? And you need to follow a key strategy or key plan. All right, so the way we're going to do this one here is we're going to note that at this stationary point here, we've got a 0 gradient. So if on the same axis, I'm going to put dy dx, well, actually, I'm not going to do it on the same axis, I'm going to do it on a different axis. I'm going to rule another one up directly underneath it. All right, and what I'm going to say is at that 0 gradient, at that point, we've got a 0 gradient. So this, remember, is dy dx versus x. It's the graph of the gradient function. So it's got a 0 gradient there. So I'm going to put a 0 gradient there. Now, I assume it's 3, and I assume this is a parabola. It looks a little bit skew-if to me, but anyway, I'm going to assume parabola. All right, so on this side here, what we note is that the gradient here is negative. It's always negative. So that means dy dx will be negative over this side here. It's got a 0 gradient there, and then on the other side, on the right-hand side, the gradient becomes positive. Now, if this is a parabola as well, if f of x equals x squared, then f dash x will equal to x. That is, it'll become a linear function. So what I'm assuming here is that this parabola will become a linear function. And how's it going to work? It's going to have a negative gradient on this side and a positive gradient on this side. So that means that the gradient will be negative here and then positive here. All right, now for many of you, that will be very difficult to understand. How is this a negative gradient? Because look at it. It's a positive gradient, Mr. Miller. And hopefully you're yelling at the video going, what on earth are you doing? Okay, you just said it's got a negative gradient and you've drawn a positive gradient. Okay, so here's where it gets tricky and you have to really think about what we're doing here. This is the graph of the function y equals f of x. This is a graph of the gradient, i.e. the values of the gradient. And what I know here is that when I jam in a value, so this is 3 here, when x is equal to 3, if I jam in a value into the gradient function, so 2 or 1, remember what I'm asking the gradient function is, hey, what's your gradient at these x values? Okay, what's your gradient at 2? What's your gradient at 1? And if you look at it on the original function, what's the gradient at 2? Okay, that's a negative gradient there. At 1, negative gradient. At 0, negative gradient. Negative gradient. Okay, so you're thinking about gradient, so always mutter the words gradient, gradient, gradient to yourself. Okay, I can't emphasize that more. So what it's basically saying here is if you look at the gradient, okay, you're going to get a negative gradient all the way up here. If I jam in 3 itself into the derivative function, what it's going to say is, wait, you've got a 0 gradient there. That seems to make perfect sense. And then when I jam in values more than 3, what it's basically saying is you've got a positive gradient. So if I jam in 4, okay, into the derivative function, it's going to go, your gradient's positive. And more than 4, positive, 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 positive. All right, so there's our dy dx or our gradient graph. All right, our second one. So what we've got is a linear function here, okay, and I actually know, or because of the points, I can actually determine the function. It's not really the purpose of this, but I know that f of x equals negative, no, not negative, x plus 1. All right, and what that's going to mean is f dash x is going to equal 1 itself. That is, along this graph here, the gradient is always 1. That seems to make sense because if you take 2 points and go, hey, what's your gradient? All right, it'll say 1 no matter where I take the 2 points. So let's draw up our graph for that. All right, and here is 1 itself. We're going to draw just a straight line there. That's dy dx equals 1. Okay, and this axis here is dy dx, and this axis here is x. Okay, so it's basically saying for any value of x, all right, if you jam in this value into dy dx, it tells you the gradient is 1, the gradient is 1, the gradient is 1. And of course that makes perfect sense with a linear function, because if you go, oh yeah, I'll take 2 points there and I wonder what the gradient is, and ooh, I'm going to take 2 different points and hopefully get a different gradient, then you obviously will be disappointed. Okay, same gradient along the line. That's why linear is a bit boring. All right, a bit boring. Don't level any accusations against linear, but yeah, it's a bit boring. Whereas here, you're going to get different gradients all over the place. And to further the chaos, what we've got is a cubic over here. Over here, we've got positive gradients, zero gradients, negative gradients, positive gradients, all over the joint. Okay, so this is an interesting situation. All right, so the first thing to think about is, all right, so I've got a cubic function. All right, now cubic functions are going to turn into quadratic functions. Again, how do I know? F of x equals x cubed, f dash x equals 3x squared. The highest power goes down 1 power, okay? Or I don't know whether that's the right word, but we'll just go down by 1. All right, so that line there is not straight enough for my liking. We should have just left it. Okay, so here's the strategy for cubics. All right, so what we're going to do is note that there's a 0 gradient point here and a 0 gradient point here. Now we need to remember that this graph here is dy dx versus x. This is a graph of the gradient. Okay, so the gradient here is going to be 0 and the gradient here is also going to be 0. All right, now what's happening here? Okay, well, along this line here, what we've got is a negative gradient. Okay, the gradient is negative. Now it's very low negative, okay, and it gets higher and higher and higher and higher, hits a tipping point, and then starts to get lower and lower and lower and goes back to 0. So low negative, at this point here, it'll be its highest negative amount, and then back to low negative. Now, I also know that it's going to be a parabola, okay? So I know that between these 2 points, what I'm going to get is negative values all the way along here, and its midpoint here, roughly, it's going to have its highest negative gradient value. Okay, so we're going to get a turning point on our gradient graph actually at this point here. All right, now beyond that, what we've got is a positive gradient along here that is really big. So a positive, big positive, all the way down to an almost 0 gradient when it hits the turning point. So that is going to be that situation there, and this is going to be the same on this side. All right, and so again, note that I know that from the quadratic function, I'm going to get, from the cubic function, I'm going to get a quadratic. The final thing you'll need to know for exercise 17D is angle associated with the gradient of a curve at a point. So the gradient of a curve at a point is the gradient of the tangent at the point. All right, so at this point here, all right, what we've got is a tangent drawn there, okay, and the gradient on the function, okay, here will be the gradient of the tangent at the point. So if the following tangent makes an angle of 45 degrees with the positive direction of the x-axis, what do you think the gradient of the function is at the point? Okay, so if the angle that this makes here is 45 degrees with the positive direction of the x-axis, what do you think it will be? Well, let's do it. M equals tan theta, where theta in this case is 45. Now that we know circular functions, let's write that as pi on 4. Okay, what's the tan of pi on 4? That's 1. Okay, so what I'm expecting here is that the gradient at this particular point will be equal to 1. Let's apply it. All right, so the planned path for a flying saucer leaving a planet is defined by the equation that. The units are kilometers. The x-axis is horizontal, y-axis is vertical. Find the direction of motion when the x value is 2 and 3. Right, so when we're talking about direction of motion, what we're finding here, and it's a little bit vague, I think, is the angle made to the positive direction of the x-axis. Okay, so the flying saucer is taking off or whatever it's doing. The direction of motion will be the angle to the positive direction of the x-axis. All right, so let's say let f of x equal quarter x to the power of 4 plus 2 over 3 x to the power of 3. So I just want to turn this into something I can use with function notation. All right, so let's find our derivative function. What's it? X cubed. 4 lots of a quarter is 4 on 4, which is 1, lower the power. Yep, looks good. 3 lots of 2/3, 6/3 is 2, x squared. All right, so now we've got our gradient function. Find the direction of motion. So let's find the gradient when x is equal to 2. So f dash 2 equals 8 plus 2 squared is 4. 2 times 4 is 8. Just had a mental blank there. Is 16. All right, let's just do this also with the calculator. So I just want to show you how to quickly knock these out with the calculator. F of x equals quarter times x to the power of 4 plus 2 on 3 multiplied by. It's going to bracket my fractions to fourth order of ops. You guys should be using that shift divide template to do this. All right, let's have a look at how it was defined. Looks good to me. Okay, so the way we're going to do this is use diff. So we're going to go action, calculation, diff, and diff f of x. That gives me my derivative function. And then what we're going to do is say a derivative. Okay, so I'm using the pipe symbol from Math 3. So I'm going to go shift. No, I'm not. I'm just going to hit that pipe. And that says, whatever's in the answer slot there, can you stick x is equal to 2 into it? Okay, so that's the derivative function with x equals 2. Okay, and it goes, yeah, 16. All right, let's do the same for the second part. I'm not finished the first part yet, by the way, but f dash 3 is equal to 27 plus 9 to 18, 37, 45, I think. That was stupid. Yeah, okay. All right, so now I know that the gradient of the tangent at x is equal to 2 is 16. So basically it's saying that, you know, if this flying saucer is flying like this, all right, it flies with a gradient of 16 when x is equal to 2, and when it gets to 3, it's an even higher gradient, okay? So what we want to basically do is find the direction made to the positive direction of the x-axis at these 2 points. So for both of them, I'm just going to use m equals tan theta, and my gradient is 16 equals tan theta. Theta equals tan inverse of 16. Now we want this in degrees. So, and is there DP suggestion? Yeah, it's pretty ordinary. All right, so tan inverse of 16. Now we want to be in degrees mode. That's really important. Okay. Hello. All right, so fairly high gradient. I mean, this thing is just taking off. All right, so theta equals 86.42 degrees. All right, and let's do the same thing for 45. So the inverse of 45, this is just going to get bigger and bigger and bigger. So for this one here, theta equals 88.72 degrees. Find a point on the fly source's path where the path is inclined at a 45 degree to the positive x-axis, i.e. where the gradient of the path is 1. All right, so that's part A done. Part B, we're going to go, hey, gradient function. When are you equal to -1? Can you tell me? Can you tell me what x values you're equal to negative? No, not -1, +1. When the gradient is +1, because that's a positive. So path inclined to the positive 45. That's going to give you, so 45, that line there is going to have a gradient of 1. Okay, so basically we say to the gradient function, hey, can you please tell me, gradient function, when you're equal to +1 or when you've got a 45-degree angle to the positive direction of the x-axis? All right, so let's do it. We've got x cubed plus 2x squared is the gradient function. And I want to know when it's equal to +1 or just 1. All right, so we're going to go x cubed plus 2x squared, take 1 equals 0. And what we'd essentially want to do is solve this thing using our techniques for cubics. I think the intent of the question at this stage is to practice cubics, so we're just going to do this on the calculator. So the way I'm going to do it is get the diff. So I'm going to go solve. I'm going to go, this is the derivative function. When are you equal to 1 for what values of x, hey? And it goes, all right, I'm in a couple of times. I'll be 1 at 3 different points. So this is going to be x equals -1 and x equals -√5 onto take away a half and x equals √5 onto take away a half. Okay, so it's got 3 instances. The cubic function has got 3 instances where it's got a gradient of 1. Now, why is that? Well, here we're going to have a gradient. Why is it 3 instances? Is it a cubic? Oh, it's a quartic, okay, a quartic. So what's going to happen, I don't know what the quartic exactly looks like, but let's just say it's something like that. And I'm looking for when it's got a gradient of +1. It should be like there. Ooh, I'm struggling with this one. There. When else? All right. I'm going to draw it and find out. Okay, so you're seeing live problem solving here by Mr. Miller. So I've got 3 proposed instances where this function has got a gradient of 1 times x to the power of 4 plus 2 on 3 times x to the power of 3. Let's just make sure my brackets are okay. All right, so 1, 1, f dash x. Let's graph the gradient function. All right, so we can see here, so this yellow graph here, or this orange graph here, is the gradient function, and we can see 1, okay, so 1 happens there, so that means that the gradient is 1 at exactly this point. Very quickly after, it also returns to 1, so it's going to be a gradient of 1 there, and then finally it happens here, they've got a gradient of 1 here, so it's at that point there. So there's my 3 separate points. All right. So we're not fully answering this one. So find a point on the flying saucer's path where the path is inclined at 45. So this is the mathematical solve, okay? But what we're going to say for the answer here, but x is greater than 0 according to the function. So if you look at the function itself, it says for values of x greater than 0. So it only happens once at x is equal to √5 on 2 take away a half, because these two solutions here are both -, numbers. All right. And part C, are there any other points which satisfy the situation? So there are on the function. So C has that point there and that point there are included, but not in domain. Okay, so they would in theory be gradient 1 points, but they're not included.